This is a production of the Chemical Education Material Study.
This is a high-temperature laboratory where researchers study the chemical properties of substances from 1,000 to 2,000 degrees Celsius, which is 1,300 to 2,300 Kelvin. Let's look at some simple substances that remain solid above 1,000 degrees Celsius, also called centigrade. How strong are their bonds, and what makes them so strong? Here are tungsten boride, boron carbide, cerium sulfide, dititanium trioxide, and titanium monoxide. One of the researchers in this field is Professor Paul Gillis.
Let me try to give you an idea of how our research proceeds. Here is a high-melting substance on which Dr. Hugo Franzen and I are working. It is titanium monosulfide. It is prepared by heating together powdered titanium and powdered sulfur. Its structure, as obtained from X-ray diffraction studies, is shown by this model. The red ones show the position of the sulfur atoms, and the silver ones show the position of the titanium atoms. As the model shows, each sulfur atom is surrounded by 6 titanium atoms. 1, 2, 3, 4, 5, 6. Each titanium atom is surrounded by 6 sulfur atoms. 1, 2, 3, 4, 5, 6. The number of sulfur atoms and titanium atoms is the same. The formula is TIS. Now, titanium forms other sulfides also. When we heat them, however, they all decompose to TIS. Therefore, we're studying TIS. What happens when we heat it? Well, that depends on how we do it. If we heat it in air, of course, it burns. But in the absence of a reactive gas, it melts at a very high temperature, about 1900 degrees centigrade. Just like any other substance, if we heat it hot enough, it vaporizes. So let's study the vaporization process to see if we can find answers to questions such as these. During the vaporization process, are all the bonds broken so that we have only gaseous titanium and sulfur atoms? Or do we get some TIS molecules? And if we do, how strong is a bond that holds this molecule together?
Let's look at the periodic table. Since titanium is in group 4, perhaps TiS2 molecules will be formed in the gas. Only research can tell. We shall use this instrument, a mass spectrometer, to determine experimentally what molecules are present in vaporized TiS. To do so, we must arrange to heat the sample. The titanium sulfide sample is put into a tungsten crucible. This is fitted with a lid having a small hole. The crucible is then placed in the heating assembly. These tungsten ribbons will act as heaters. Around the crucible is placed this heat-insulating device consisting of several concentric metal cylinders. This vertical slot will enable us to observe the crucible during the experiment.
Now, when the assembly is complete, we can insert it into the mass spectrometer. In the mass spectrometer, a vacuum of about 1/1000th of an atmosphere is reached after pumping for 3 or 4 hours. We'll use a magnet to raise a metal flap so that we can see through the slot. The tungsten ribbons begin to glow as electric current flows through them. They heat the sample to about 1,000 degrees centigrade, but we need to go much hotter. To make it hotter, we apply a high voltage. Let's see in animation how we do it. Here is the crucible with its surrounding tungsten ribbons through which the heating current is flowing. The crucible is now connected to a source of high positive voltage, causing electrons to leave the hot tungsten ribbons and to bombard the crucible. When these fast-moving electrons strike the crucible, their kinetic energy is converted into heat, which further raises the temperature. Now we need to measure the temperature. How do we do that?
We use an optical pyrometer, which we have aligned and focused so that the glowing sample is visible through the optical system. The pyrometer contains a red filter which increases the sensitivity of the instrument. By moving this knob, we can adjust the temperature of a hot wire within the pyrometer so that the wire's brightness, and therefore its temperature, matches that of the sample. The center of the hot wire becomes invisible when the temperatures are equal. The temperature reading on the middle scale and the time of observation, like all data, must be carefully recorded in a notebook. Then we apply suitable corrections, evaluated by calibration experiments. They total to 41 degrees in this instance, to give the corrected temperature in degrees Celsius and Kelvin. The final value, 1805 Kelvin, is accurate to plus or minus 5 degrees.
Having achieved our high temperature, we shall now use the mass spectrometer to analyze the gas vaporizing from the hot sample. Molecules of vapor escape from the crucible through the hole in the lid and pass through the mass spectrometer. A shutter can stop the beam so that we can distinguish between molecules originating elsewhere in the apparatus and molecules originating in the crucible. Now we'll keep the shutter open and run the mass spectrum. A combination of electric and magnetic fields within the instrument sorts out the gaseous molecules according to their mass. This recorder indicates the mass and relative quantity of various molecules passing through the spectrometer. As the chart paper moves, it records the arrival of molecules at a detector. Molecules of low molecular weight are recorded first, then progressively heavier molecules as the chart moves along. Molecules of different masses are recorded as separate peaks on the chart. The position of the peak on the chart is a key to the mass, and therefore the identity of the unknown molecule. The relative height of a peak is a measure of the relative quantity of that kind of molecule present.
Most of these peaks obtained with the shutter open come from the background gases. Experiments with the shutter closed show that only these three come from the material in the hot crucible. To show these significant peaks, we have a separate tracing of the spectrum. We have eliminated all the background peaks, and also those arising from the different isotopes of titanium and sulfur. The peak at mass 32 comes from sulfur. The peak at mass 48 comes from titanium atoms, and at mass 80 from TiS molecules. If TiS2 molecules were formed, they would appear at mass 112, but we found none. As you can tell, TiS is a principal constituent of the vapor at this particular temperature. The relative peak heights, and hence the pressures of TiS and titanium, are very nearly in the ratio 2 to 1, actually 2.10 with an experimental uncertainty. The pressure of sulfur and the pressure of titanium are the same. Well, we've answered one question.
TiS vaporizes to give titanium atoms and sulfur atoms. Also, it vaporizes to form TiS molecules. Now, we also saw that the pressure of TiS molecules is 2.1 times the pressure of titanium atoms at this temperature, which you remember is 1805 degrees Kelvin. Now that we know what happens, we can proceed to measure the bond strength. To do that, we make measurements at different temperatures. Now, what would you expect would happen? Well, here are the results. We have used the mass spectrometer measurements and have plotted the ratio of the pressure of TIS to that of TI as a function of temperature. Here is the 2.1 to 1 value at 1805 degrees Kelvin. As you can tell, the proportion of TIS in the vapor decreases with increasing temperature. We now have information about the relative amounts of the constituents in the vapor phase. In order to get the bond strength, however, we have to know the actual pressures of these constituents.
This torsion effusion apparatus is designed for that very purpose. It operates on the same principle that drives rockets through space. Here's how it works. In the center of a metal cylinder, which will act as the heater, is the crucible containing the TIS sample. The crucible is rigidly attached to a tungsten rod, which in turn is attached to a mirror, and then to a very thin tungsten wire known as a torsion wire. The position of the mirror is measured by this telescope and scale. The experiment is conducted in an evacuated glass tube. A copper coil carries a large electric current which reverses direction several 100,000 times a second. This alternating current induces electric currents in the heater. The temperature rises. Heat from the cylinder is radiated inward to the crucible. The gas, produced from the vaporization of the hot sample, escapes through the holes. The resulting jets rotate the crucible, the rod, and the mirror, and twist the torsion wire. The angle of rotation is directly proportional to the pressure of the escaping gas. Here is the assembled torsion apparatus in action. Of course, the actual crucible is obscured by the hot metal cylinder, which is visible inside the heating coil. As the sample gets hot, the crucible turns, and the wire and the mirror twist. When they stop, equilibrium has been reached. We take a reading of the scale as reflected in the mirror. This indicates the amount of twist. The calibration of the apparatus enables us to calculate the total pressure from the amount of twist. Now, from the mass spectrometer data, we know the relative proportions of the gases present at this temperature. Hence, we can calculate the pressure of TIS and the pressure of titanium, which is equal to the pressure of sulfur. Additional experiments at different temperatures enable us to calculate how the pressures of the individual gases vary as temperature changes. This variation is intimately related to the bond strength of gaseous TIS through Le Chatelier's principle.
Here are the data for gaseous TIS. The logarithm of the pressure of TIS is plotted against the reciprocal of the absolute temperature. Here is the area of high pressure, and here, low pressure. Here, high temperature, here, low temperature. This plot for solid TIS forming gaseous TIS indicates high pressure at high temperature, falling off rapidly as the temperature falls. The logarithm of the pressure decreases by 1.28, while the reciprocal temperature is increasing by 5 times 10 to the minus fifth. The change of pressure with temperature is related to the heat of reaction. In fact, the heat of reaction, delta H, is equal to a constant K times the slope S of the experimental curve. The constant is equal to minus 4.58 times 10 to the minus 3, which has been determined from other work. The slope of a curve is defined by the ratio of its vertical component to its horizontal component, or the slope is equal to minus 1.28 over plus 5 times 10 to the minus fifth, or minus 25.6 times 10 to the third. The heat of reaction is 117 kilocalories. Thus, delta H for this reaction is 117 kilocalories. Similarly, we find that delta H for this reaction is 240 kilocalories. Now, in order to get the bond energy, we subtract these two reactions and their heats. TIS gas reacts to form Ti gas plus S gas, and its delta H is 123 kilocalories. Now, what is this 123 kilocalories? That is the energy that must be added to 1 mole of TIS molecules in order to dissociate it into its constituent gaseous atoms. We have measured, using similar techniques, many bond dissociation energies. For example, the bond energy for TiO is about 35 kilocalories larger than for TIS. Just why this is so is a subject for future research.
For example, consider one high-temperature problem with a space shuttle. Air friction on re-entry raises the bottom surface to high temperatures, like those explored by Dr. Gillis. So insulating ceramic tiles have been developed which can prevent the heat from reaching and destroying the main shuttle shell. But shuttle tiles are brittle. One of the most active fields of current chemical research is ceramics, which will withstand high temperatures and not crack under mechanical stress. Turbine blades and jet engines are typical examples of such needs. High-temperature processes are becoming ever more common as our knowledge expands.